Let's say I have a ball. I have a ball. Now I throw this ball up, and I throw it up with a velocity of 10 meters per second. So this ball goes up, and it comes back down after some time. And after some time, it falls back down to the same level, and then it continues downwards. So that's the experiment that I'm trying to imagine at the moment. What I like to do is to think about the velocity time graph and think about using it to find things like distances and maybe velocities and or accelerations at the same time. So now let me suppose that after 1 second the ball has reached the top. Okay, the ball has reached the top, and then it falls downward, and after another second it has reached back to the same level. Okay, and then it continues downwards. And let me suppose that when it comes back down to the same level, it also has a speed of 10 meters per second. We'll learn later on when we talk about Newton's law about why it comes back down. When it comes back down, the speed is the same. Okay, all right. So the next thing I want to do then is to sketch a velocity time graph of this experiment. See what it looks like, and then and also see what I can do with it. So that's the time axis, the time in seconds, velocity axis, velocity in meters per second. That is the origin. Okay, so in the beginning, we are here in the beginning, and I want to think about let's see, that would be the start of time. Okay, this is when t is 0, and when t is 0, the speed is 10 meters per second. Now, because we are going to talk about velocity, we need to think about direction. In this case, since it's a vertical motion along a vertical line, okay, along a vertical line, I can represent the direction using positive and negative values of displacements and velocities. So let me just choose either up or down as positive. I'll choose up as positive. It really doesn't matter as long as I stick to it. So therefore, the starting velocity, since it's going upward, has a positive sign, so it's plus 10 meters per second. When it comes back down to the same level, it would be minus 10 meters per second. And when it's right at the top, it should be 0 meters per second. Okay, so then we can try and plot our graph at 0 time. All right, when we are here, the velocity is 10 meters per second. So we are there. Let's say that's 10, and after 1 second, it reaches the top, and reaches 0 velocity. So let's say we are somewhere there, okay, and that's 1 second. And after another second, it comes here. It comes to a velocity of minus 10. So that's after another second. So that means we are at 2 seconds now, and the velocity is minus 10. So somewhere there, okay, I'm just sketching roughly. So that's minus 10. So the graph is, therefore, the graph is in this case, okay, it's roughly a straight line. Let me try and draw this. It's roughly a straight line going through these points. Okay, that doesn't look very straight. Okay, let me try again. Something like that. Okay, it's a straight line. And what I want to do now is to find the displacement as well as the distances traveled. Let me start with the first second down here. Now, in the first second, the displacement we have learned previously, displacement would be given by the area under the graph. So that would be this area. So what would this area be? It would be the displacement. This would be the displacement now. And I can find that quite easily because it's a triangle with a base. The base of this triangle is here. The length is 1 second. Okay, so it's a bit strange. We're not talking about centimeters or meters here. It's actually 1 second. Alright, that's the kind of a length, but it's not really a length. But we're pretending that it's a length. Okay. And the height is 10 meters per second. So again, this is not really a length. It's a velocity, but we're pretending to be a length because this shape here is a triangle, and we can find the triangle by taking half base times height. So half base is 1 second times height is 10 meters, and the answer is 5. And because we know the area is a displacement, so the units must be meters. Okay, and it sort of agrees if we think about taking multiplying the units for meters per second and second together. Yeah, we do get meters. So that's the displacement. Now, while we are here, let's be careful about this displacement idea. Displacement is a vector, so therefore it has direction. So what's the direction of this displacement? Well, since the ball is going up, since we're talking about ball going up, the displacement should be positive. So I should have a plus sign there. Okay. Next, I'm going to look at the ball coming down. Right, the ball on its way down. What is the displacement on its way down? I can find that from the graph. Now, on its way down is this part of the graph. But what would be the area that we're talking about? Well, it would be the area between the graph and the horizontal axis. This would be the area that we want. Okay, because after in each short time interval, right, this part gives us the velocity at that time interval. So the area here would be the velocity times the time. Only thing is it's going in the negative direction, right? That's why the graph is below the time axis. But that's fine. All right, we can still find the displacement in this case. So displacement. The displacement in this case would be, let's see, again half base times height. So half times the base of this triangle is here, is this length from 1 to 2 seconds, so it's also 1 second, and the height of this triangle is, in this case, minus 10. So there's already a sign, minus 10 meters per second. Okay, so it's half times 1 second times minus 10. And the answer is minus 5. So the sign is there already, and you can see that it agrees with what we know about the downward motion. Okay, downward motion is going towards the negative direction that we have defined. So therefore the displacement is minus 5 meters. Okay, so they all fits, and we now even have an understanding of how to deal with the velocity time graph, how to deal with finding the displacement and area when the graph goes below the time axis. Okay. Now finally let's do something interesting. Let's think about the displacement over 2 seconds, all right, from 0 to 2 seconds during this time interval, meaning all the way from the start to the top to the bottom. All right, let's think about this full motion, up, going up and coming down again. So how can we find this from the graph? How can we find the displacement from 0 to 2 seconds from the graph? So let me write this down. That's what I'm interested in. Displacement. Well, I have a graph that goes all the way from there to there. Okay. But I know that we know that we can find the displacement by finding the area under the graph. But in this case, this part of the graph, the first part of the graph has this area under it. The next part of the graph has this area, which we now know is the displacement in the opposite direction. So what do we mean by area under the graph? All right, they're on different sides of the time axis. That's rather odd. Well, the way to do it, okay, is to add up these two areas, add up this area and this area. Okay, to total up the area. That will give us the displacement between 0 and 2 seconds. Now, how do we total up the area? Right, we make use of the previous result. This area is, we have already found, is given by the plus 5 meters. And this area, we have also found, is given by the minus 5 meters. So therefore, the total displacement would be plus, I'll write it down here, will be plus 5 meters from there, minus 5 meters from there. And so we have the answer now. The answer is 0 meters. But does that make sense? 0 meters? This ball has gone up and come down and the displacement is 0 meters? Well, actually, yes, because if you remember, with the overall distance, displacement is always obtained by joining the starting point directly to the final point. And in this case, after the 2 seconds, the ball went up and came back down to the same level. So therefore, it the overall displacement is actually 0 because it's back to the same place as the starting point. All right, so the overall displacement therefore is 0, and therefore 0 meters is the correct answer.